In this video, we discuss graphing polar equations. And this is the method that I use. You can also use a graphing calculator to do this. Um, this is how I would graph a polar equation if I was graphing it by hand without a graphing calculator. First, if I'm given a sinusoidal function like 4 sine of 3 theta, I would graph that sinusoidal function in the r theta plane. Knowing what I know about sinusoidal functions, it's pretty easy for me to graph a constant times sine of a constant times theta, or a constant times cosine of a constant times theta. Or if this was shifted left or right or up or down, I would be able to graph it pretty simply. So I'll graph that sinusoidal function in the r theta plane. Then I'll use my graph to create a table of values, and then I will take that table of values and plot the points on polar plotting paper. Now, if necessary, I might have to add more points to my table, add more values to my table until the graph starts to repeat itself. Because this is a polar equation, eventually the graph will start to repeat itself. It's just hard to tell on the surface where it would start to repeat itself. So that's the plan. Let's go through that process for this polar equation. R equals 4 times sine of 3 theta. Now, in order to graph the sinusoidal function in the r theta plane, I'm just going to start with the graph of the sine function. Now, y equals sine of x just looks like this. It starts at its max, or it starts at 0, it goes to its max, then it goes back to 0, then it goes to its min, and then it goes back to 0 again. And normally the range is -1 to 1, and the domain for one period is 0 to 2 pi, and then it repeats infinitely in both directions. Now I'm just drawing one period here as well, but if instead of having a 1 out front, if I've got a 4 out front, well, that's going to take that -1 to 1 interval, and it's going to make it the interval from -4 to 4, because I'm stretching the whole thing by 4 units. Rather than making it taller, I'll just label my tick marks differently. So the r values on this graph go from -4 to 4. Now, this 3 over here affects the period. If there was no 3 here, if it was just sine of theta, the period would be 2 pi. But since there is a 3, the period is 2 pi divided by that value. So in this case, that value is 3. So we get 2 pi over 3. Now, all of the interesting things happen at 1/4 of the period. Interesting things being zeros, maximum values, and minimum values. So half of the period is where it's 0 again, so that's pi over 3. Half of that is where we're going to be at the max. And then we're going to take pi over 3 and add that to get, that's 3/4 of the period. Taking half plus a fourth to get 3/4. So this is pi over 6 plus 2 pi over 6 is 3 pi over 6, which you can simplify to pi over 2. But it might be simpler to think of this as pi over 6, 2 pi over 6, 3 pi over 6, and 4 pi over 6. Just because you can see it increasing by that 1 pi in the numerator every time. And the denominator staying as pi over, staying as a 6. Okay, so this is my graph, and we know it repeats. To make my table of values, I'm going to use an increment of 1/8 of the period. If I use an increment of 1/8 of the period, what that's going to do for me is it's going to get the points on the graph that are the interesting points. So the 0, the max, the 0, the min, and the 0 from that original sine function. And if I use eighths of the period, it's also going to get me that value and that value, and that value and that value. And because of symmetry, we'll be able to simplify some of our computations. So I'm going to call my increment 1/8 of the period. So that's 1/8 of 2 pi over 3. And that simplifies to pi over 12. And pi over 12, Let's see what that is in degrees. So 180, oops, 180 over 12. So that's 15 degrees as our increment. Okay. And we're using that increment to create our chart. So R is going to be equal to 4 sine of 3 theta. And we want theta, the theta values in our chart, to start at 0 and increase by 15 degrees every time. So I'm going to leave theta in degrees temporarily, and then we'll convert to radians. So I just keep adding 15 degrees. And 120 degrees is that full period, 2 pi over 3. Now we might need more values for our table, but we know after a full period, at least these points are going to start repeating themselves, even if the points in the polar plotting paper don't repeat themselves. So let's figure out what R would have to be at each of these angles. We'll have R equals 4 sine of 0. Sine of 0 is 0. And actually, we can just read this graph. Let's skip all the multiples of 15 degrees and just stay at the multiples of 30 degrees. So we'll have 0, then we'll get a max of 4, then 0, a min of -4, and then 0. So I have 0, 4, 0, -4, and 0. Okay. And now let's add in those multiples of 15 degrees. So 15 degrees times 3 is going to be 45 degrees. So we'll have 4 times sine of 45 degrees, which is square root of 2 over 2. So we get 2 root 2, and root 2 is approximately 1.4. See, and then we multiply by 2. Sorry about that reflection. We get 2 root 2, and my calculator gives me approximate 2.8. Now look at the symmetry. Are we going to get 2.8 over here as well? If you're not sure, actually substitute in that 45 degrees and see what you get. But I know from my picture that sine is positive, so we're going to get approximately 2.8 there. And then over here, it's going to be the same value, but with the opposite SIGN sign. So we're going to get -2 root 2, which is approximately -2.8, and -2 root 2, which is approximately -2.8. Okay, so now I've got all of my values. And now it seemed like we were doing a lot of work, but it's really 0, max, 0, min, 0. And we find those two values, and then we use the symmetry of our graph to infer that these two are the same and that these two are the same in absolute value, but opposite sign of those two. Okay, so we're here, and we'd like to plot all of these points. So we're going to go to our polar plotting paper and start graphing. Now what's a little different is you start with the theta first, and then once you're on that ray, you go out this many units along that ray. And if the R value is negative, instead of going in the direction of theta, you go in the opposite direction. So here's my paper. And it looks like our first point was, oops, you can't see that. I'm going to fold it for you. Our first point is 0, 0. So when theta equals 0, R equals 0. We start right there. Then when theta equals 15 degrees, R equals 2.8. So we go out to the 15 degree line, and I really need a straight edge for this, don't I? I'll use a piece of paper as my straight edge. Sorry about my nails, they're looking pretty bad. Okay. We go out to the 15-degree line, which is right there, and we go out 2.8 units from the pole. Just to make everything a little bit bigger, let me see if I have enough room to do 2 units as R. So I'll go R equals 1, R equals 2, 1, 2, 3, 4. Yes, the maximum value of R is 4, so we can do that. So this is R equals 1 by choice, R equals 2, R equals 3, and that's R equals 4. We want to go out 2.8 units along this line. So 1, 2.8. So we've got that point, and we've got that point on our graph. Okay, next one, 30 degrees and 4. So we go to the 30-degree line. We go out 4 units. So there's 1, 2, 3, 4. Okay. Then we go to the 45-degree line and we go out 2.8 units. So that's 1, 2, 3, 2.8 would be approximately right there. Then at 60, we're back to 0. So we're here. And then at 75 degrees, we go to negative 2.8. R is negative 2.8. So we're on the 75-degree line, but rather than going out in the direction of that 75-degree ray, going out 2.8 units that way, because R is negative, we go in the opposite direction. So I'm going to go out negative 1, negative 2, negative 2.8 right there. Okay. Then at negative, I wrote negative 80. It's not right. I'm supposed to add 15 degrees. How did I do that? Should be at 90, and then 105, and then 120. I don't know how I made that arithmetic mistake, but I did. Okay. All right. At 90 degrees, R is negative 4. So we're on the R equals, or the 90-degree line. That's what used to be the y-axis. But rather than going up 4 units, we go down 4 units. So we go 1, 2, 3, 4. And then at 105, we go negative 2.8. 105 is right here. So rather than going 2.8 units this way, we're going to go 2.8 units this way, negative 1, negative 2, negative 3, 2.8. See that symmetry? Sort of looks like a flower. And then we go back to 0. Now it didn't start repeating itself, so let's keep going. So I'll do add 15 degrees, add 15 degrees. And so on. So at 135, we're going to be at 2.8 again. And at 150, we'll be at 4. Because basically what we're doing right here is when our sinusoidal version would start repeating itself. That would be the next period. So we're just going to pick up right here. It's sort of where we left off. But these angles are going to be incorrect. So our angles will be 135, 150, 15 more than that, 15 more than that, and so on. But the R values are going to repeat. So R is 2.8, 4, 2.8, 0, and so on. And we want to keep doing this until we see repetition in the XY, or in the R theta plane where we're graphing this. Or not R theta plane, but in the polar plane. Okay. So at 135, we want to go out 2.8 units. There's 1, 2, 2.8. Then the next one at 150, we want to go out 4 units. 1, 2, 3, 4. And then at 165, we want to go out 2.8 units. So 1, 2, 2.8. And then we're going to be back at 0. And then we add 15 again. So you're going to be at 180. And then you're going to go out negative 2.8 units. So at 180, you go 1, 2, 2.8. Wait, no, wait, that's not right. At 180, we're back to 0. And then it's over here at 195 that we go out 2.8 units, negative 2.8. So we end up there. So at 195 is when we start to repeat. And so what the graph looks like is this. It's kind of like a flower. And 195 was when we got back to that first point right here. So I guess you could say that we traced out this whole thing on the interval from 0 to 180, 0, and then we went 0, 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, 180. And then at 180, we started repeating again. So this starts repeating itself every pi radians. Even though a little flower graph starts repeating itself every pi radians, even though the original sinusoidal function, r equals 4 times sine of 3 theta, repeated itself every 2 pi over 3 radians. So be careful about that. The period of the sinusoidal function is not necessarily the period of that polar graph. Like that polar graph will be completely traced out eventually, and then it'll start to repeat itself. But it won't necessarily repeat itself at the same value of theta as on the original. The r values started repeating themselves at 135, but with different angles, we ended up plotting different points on our polar plotting paper. Okay, so that's how we do that. It turns out that this is sort of typical. If this is sine of n theta, and n is an odd number, we get a flower with n little petals like this. And there are more pretty graphs in your book, and it tells you sort of all the patterns for different values of n and sine and cosine and all of that.